Thank you for the introduction. I'm Umeda of Tokyo University. I will be giving my talk in English. The topic is supporting human engineering activities by the digital triplet. From April of this year, we established a Center for Engineering on research into artifacts. We are looking into manufacturing of the future. Our center was refurbished in order to focus on this topic. I'll be talking about the approach of the digital triplet and how we can digitalize manufacturing systems in the future using this concept. In the West, there's a lot of talk about the learning factory concept, where you have a factory inside a university used for engineering. You have a factory in a university for education, and you do experiments jointly with companies. Unfortunately, there hasn't been such a trend in Japan, but we'd like to make something like a learning factory and do research on manufacturing from a Japanese perspective. I'd like to share some of our research results today. We think there are two topics that are particularly important. Firstly, Industry 4.0 and other types of new approaches to manufacturing called digital transformation need to be used to revolutionize manufacturing. However, this digital transformation of manufacturing has not really fit with the style of Japanese manufacturing so far. It seems like digital transformation is going in a different direction than we would like in Japan. There are some important points in digital transformation. The first is to exchange data through a network between multiple companies in order to increase the value. Secondly, there's a need for a standardized digital platform which can be used for exchanging data. These are areas that Japan is lagging behind the rest of the world in. The second issue is that manufacturing engineers and technicians have had trouble keeping up with digital transformation. This problem may not be limited to Japan, but it is noteworthy here. In future digitalized manufacturing systems, the main system engineers will need to carry out various activities such as planning and designing and developing manufacturing systems, as well as constructing them, operating them, maintaining them, and improving them, and replacing them, utilizing not only the physical world, but making good use of the cyber world. We need to be able to do that, but Japanese engineers are not sure how to utilize cyber technology for these missions. Let me explain what we think about this. I don't have much time to talk today, but when we think about the mega trends, Japan's previous strengths of mass production of high-quality products is not enough. We need to establish a new manufacturing strategy. In particular, the strengths of Japanese manufacturing need to be planted into the new vessel of digitalization, such as IoT and cyber-physical systems and AI. What are Japan's strengths in manufacturing? This is something we need to discuss, but tentatively, I think as follows. Japan has always pursued high-quality production. The high-quality products with zero defects have helped to reduce the cost of production systems. Japan's strength has always been kaizen, or continuous improvement. In the digital age, we need to continue to be able to achieve such continuous improvement. If I have time later on, I'd like to touch upon another topic. We need an educational curriculum that enables continuous improvement in the digital sphere. IoT and CPS and other technologies are, of course, important, but conventional manufacturing technologies and processing technology are also important. Meanwhile, system thinking is also very important, I think. I will skip this slide. We have the concept of the digital triplet. Industry 4.0 tends to take a top-down approach and works very systematically to achieve automation, we believe. Cyber Physical Production Systems, or CPPSs, do not necessarily get improved frequently. That's not assumed. CPPS plants are built with enough margins and robustness to run unchanged for a considerable time. In this way, we try to automate where it's possible to automate. But to complement that, we need to make use of Japan's strengths, such as its knowledgeable engineers and their experience in improving the systems. We need a CPPS that can be amenable to continuous improvement, or Kaizen. We need CPPSs that can improve themselves over time. That's what I refer to as the digital triplet here. This might be a little bit hard to understand. Not everybody likes this diagram, but here's the image of it. There's a physical world and a cyber world. That's referred to as a cyber-physical system, or the digital twin. But in addition to that, we have the world of people using these systems. I call this the intelligent activity world. These three spheres are combined to form a digital triplet. We focus on supporting people so that design, manufacturing, use, maintenance, and circulation can be carried out more effectively. The entire product life cycle will be supported. The physical world and the cyber world will need to be used in an optimal manner to maximize value. That is what we refer to as the intelligent activity world. We want to make a triune system that optimizes all of these aspects.
So if it's the case, the engineers here, it stands to reason that all these engineers have to take advantage of both the physical and cyber world. So the Kaizen activities, or the maintenance of or design of production systems or product design, everything that is true in everything. But so first, they capture the information from physical world, and so by making use of that, a lot of tools and AI and simulators, and they analyze that's the physical world, the data, and make the decision, and coming up with the solutions and actually implement it. So this is we call it engineering cycle. It's shown here in the yellow cycle. So the industry 4.0 is that we need to just to check out and to validate this cycle. So that's why the engineers on the floor have to build up their own cycle like this. And so this will be then actually reflected in the physical cyber intelligent activities. So you can create one value if it go in this cycle once, and for example, and lower the defect rates and improve the productivity. So that's why, and we'd like to support that. We're building up this cycle and the structure. So that's why this one portion represents the data capture and data analysis. And what kind of data should be collected, or what kind of specific tool should be used for analysis. So this is the part of the engineering process, and we need to support in the building up all these system analysis. So in order to do that, and we have to have a button over this, the process intelligence, as in we have to collect this process intelligence for the engineers, how we can acquire this information, and what's so far the experts have done. We need to acquire the knowledge of the experts into the system. So this means this is that we need to first the standardize, and that is about the process, and also we need to just deploy the knowledge. So that eventually we need to support that the intelligent activity of the human workers and engineers, and like to roll out this idea to the outside. So what we're going to do is that, in a sense, the AI will replace that expert's knowledge and activity, but it's not that, but now if we just reflect that and all this, the human thoughts and the human activities on the AI, and we try to replace that all this human activity, the human knowledge as much as possible with AI, and eventually that when all the engineering process will be digitized, and then we can add more added value. That will be the specific process we'd like to establish. So, if in the case, the first of all, we need to have that kind of the expert process has to be copied and put down on this here in this area. I'm sorry. So this is one of the example is about the molding die. I'm sorry that this is some of the confidential and slides, and I didn't think that I have such a big audience, but this is that some of the, in order to eliminate that's the defects of the molding die manufacturing. So some experts have the design and the manufacturing design about this of the molding die and the CAD, and they try to take advantage of the expert knowledge and the experience. So this now you're looking at the engineering models we build up, and we can have a good example of this and experience and the knowledge of experts. So when it comes to Saika, what's important is that is the ground in that's the cyber physical system, and just like the digital twin. And once it's reproduced, we have to know we can know about we can reproduce it all this and experience of the experts, human experts. So this is which try to just a copy of this, and also put down the specific process of the experts. And so when they try to experiment that the knowledge can be transferred and be used by even that very a beginner's level of the workers, not the experts. So now, but our major finding is that it's not an activity being done by the older skilled workers, but also we can build up and more modernized the new process of the. So that's why, just like the experts, the process is different, but now this new engineers and the workers can achieve the results with what the older experts have done. And also, the novice scanner machine, the model was an acceptable quality with the support of the constructed EC, but now then also this expert can try the different fields. So when it comes to digital triplets, so in a broader definition, it is the part of the digital triplet is this and the CPPS. But what's in the focus is to support the human engineers, and for second, so cyberspace and cyber physical system. For this digital twin and digital space, this is the model, and that's model coming out from the physical, or it's also been divided into the human activities of the experts and experience. So this is the point, I think. So I'm going to skip these. So when it comes to this, if we make use of digital triplet, as mentioned earlier, that the learning factory for the digital physical world can be realized. And the other thing is that we can take over the knowledge of and experience of the experts, and that can be transferred to the new workers and the novice worker. And we can use that knowledge for the training and education. And at the same time, we can also reinterpret that the experts' knowledge and experience for the more modernized format. And so this is this is the challenge we're doing for this. Now we try to come up with the education curriculum, and in order to educate the manufacturing engineers. Okay, so this is the slide is about talking about the examples of what we have tried to, and I'm going to jump to the conclusion of the last slide. So first of all, when it comes to that, the digitalization in which we can take advantage of our strengths of manufacturing experience, so that's why we like to do in our the organizations here. And the first off, so by we like to have a lot of the good success stories of this digital physical world. And so that kind of all the success stories will be important for push more of this digitalization of the Japanese manufacturing, and that's why the digital triplet should be useful for the framework with which we can collect a lot of that and showcase a lot of the success cases, and they would like to reproduce it exactly the same experience in our lab or our environments. And so that eventually we would like to make a contribution to the digitalization of the Japanese manufacturing industry as a whole. That's all. Thank you very much.